Let's try number 8 in this series. I'll just read you the question. It says to calculate delta S when 3 moles of perfect gas changes state from 25 degrees Celsius and 1 atmosphere to 125 degrees Celsius and 5 atmosphere. And when we find the delta S, they want us to rationalize the sign. So to just comment about it being positive or negative and why that might be the case. So let's transpose the given information into a nice concise list here. I have 3.00 moles, it's 3 sig figs. The initial temperature, excuse me, T1 is 25 degrees Celsius, and I'll convert that to Kelvin. And the initial pressure is given as 1.00 atmosphere. And this undergoes a change, and I'm not labeling that change, for example, labeling the path, because there are a couple of things changing. So let's just continue. Of course, it's closed. N2 is equal to N1. T2 is 125 degrees Celsius. Just going to fix the focus here. This seems to make it work. I don't know why. T2. P2 is 5. And we are asked to find delta S. Okay, so what is happening? The temperature is changing and the pressure is changing. So it's not an isothermal change. There's nothing in the question that tells us that it's an adiabatic change. That would be easy because delta S would then be 0. I don't see anything being held constant. It's not isobaric. It's not isothermal. I'm not told that it's a constant volume. So what do we do in this case? Well, something that we do in thermodynamics, all the time, whether we are aware of it or not, is we are selecting a convenient path. And sometimes that's explicit because it's given to us in the question. And sometimes we have to devise one. And as you know, when we do calculus and split up a change into an infinite number of infinitesimally small equilibrium steps, if you like, along the way, that's what we're doing. And in this case, it's going to be a little more concrete. Let's consider that delta S is a state property, and so delta S is equal to the S final minus the S initial. And entropy, being a state property, is not path dependent. So it's not like I'm being asked for Q or work. You might be thinking, well, hold on, Q is a part of the definition of binding entropy, and you'd be right, absolutely right. But it's not just any heat, it's the heat associated with the reversible, right? The process. It's Q reversible. So in fact, it is not path dependent. It is a state property, delta S. So having said that, I can devise a convenient path for this change that's kind of a compound change. How about we let, first of all, in the first step, let's break this into 2 steps. And that'll be our convenient path. And in the first one, let's make it reversible, since to find delta S I need the reversible Q. So let's connect these 2 states, 1 and 2, first of all with a reversible heating that would be isobaric. So let's keep the pressure at 1 atmosphere and just get the temperature up to 125. And then in the second step, let's keep it isothermal. Yeah, you got it. Keep it isothermal at 125 and change the pressure. So let's do that. It doesn't matter which step you do first, no. And so let's just do what we said. Let's do isobaric reversible heating followed by isothermal reversible. Reversible what? What would it be called? If you're at 125 and you want the pressure to go from 1 to 5 isothermally, yeah, you'd have to be changing the volume. You'd have to be compressing at 125 in order for the pressure to go up. Yeah, so the second step will be a reversible isothermal compression. Let's list that out. Let's actually put it right here. So little guy I, the first one will be reversible isobaric heating. I have to say it slowly just to make sure that I'm labeling it right. And then the second step, so once we get the temperature from 25 to 125, we'll keep it isothermal. This is a really good question, say for an exam, because you really have to think about problem solving here. Yeah, you don't get to plug it in right away. And that's the level of expectation come to the exam on this stuff. So this is really good. Reversible isothermal and compression. And I hope you're all convinced that that is, in fact, a compression. So to get the pressure up isothermally, you'd have to change the volume. You'd have to compress the volume. So my delta S then will be equal to the one of the first step plus delta S of the second. And I am avoiding calling that total because total is kind of reserved for system plus surrounding. Yeah, so I'm just going to put delta S. It clearly is for the system, but it is for the system that undergoes these two steps. So let's start with the first step then and decide how I would calculate entropy change for that. And let's just start with our definition. It's the dq reversible over temperature. But I'm heating, right? And so my q reversible, it's isobaric, so this is really dq sub p, and dq sub p is my enthalpy, so this is dH, and I know that dH is N CV or CP? CV goes with internal energy, CP molar goes with enthalpy. Now be careful before you write delta T here. Remember, I'm in the small change regime, and so this is dt. Haven't integrated it yet. Okay? And that happens all the time because you know what formula you're going to use. You see it already and anxiously get to that step, but just be patient. Okay? And then I integrate this. Okay? And I get that being delta S. Again, it's under the umbrella of I, so this is delta S for the first step. And that is equal to, what can I pull out here? N. And yes, I can pull this out. And when I do that, I'm assuming that the heat capacity is constant over the change dt. Temperature is changing. Remember, I'm heating. And the integral of 1 over t dt is ln of t final minus ln of t initial, or the ln of that ratio. And so I have a ready formula to plug into. Again, if you knew this immediately, you could jump to this formula because nowhere in this question is it asking you to, starting here, devise a formula. But that is something that you need to be able to do. Yeah, so that's ln. T final, well, we were using 2 and 1. So that's, well, T2 over T1. And now we're ready to put in our information that's known. So delta S is equal to, I have 3 moles, and the CP molar, of course, is 5/2 R, and the R value I'm using, I wouldn't use the liter atmosphere per mole Kelvin, right? Because that's going to introduce units that I don't need. 8.3145 joule per mole K, right? And then I'll be left with joule per Kelvin, which are my units of entropy, because of course this is unitless. Now, just to push the point home here, because this is instructional tutorial, I am going to put T2 as 125 plus 273.15 Kelvin, T final, over T initial, 25 plus 273.15. You don't have to do it like this, of course not. I'm doing it like this. I think you can appreciate why. Because as a video, I'm just reminding everybody they need to convert those temperatures to Kelvin. I'll share with you, I know, sorry, tongue-tied. I'll share with you a common mistake that I see on the exam, especially when initial temperatures are above 100, when they're already 3 digits. People forget to convert them to Kelvin, especially if it's like 200 or 300 Celsius. Yeah, so just be careful with that, and also make sure you cross that out. Okay, so we're ready for the calculator. And, well, that's 298 and 398. So 398.15 on 298.15, 1.33. I'll take the ln of that. And then I'm going to keep going. Times 8.3145 times 5 divided by 2 and times 3. I get 18.036. Is that what you have? 18.036, my units, joule per Kelvin. Sig figs, should I trim back at this stage or just leave it? Let's just leave it because I'm going to be adding, and so it's really stored. But actually it's not going to make a difference. And then the next step, when I add, I would have too many decimal places. So let's make sure that it is 3 sig figs at this stage. And that'll be 18.0. How about the sign? You want to double check the calculator and make sure that the sign is not missed on the screen, and check it with the procedure itself. So in this first step I'm heating, so I do expect that when I heat and introduce Q that the disorder level increases and I have a positive value of delta S. Okay, so let's continue with the second one. And yeah, so maybe I will just put that there on that one. Okay, so for the second one, this is now a reversible isothermal compression. I'm going to start it the same way. It's kind of a good review to go through this anyway. Always my starting point, and I say it's kind of a useless formula, but a very good relation, because as a formula I can't plug into it. Okay, isothermal, great, temperature is constant, so I'll be pulling that out. And it is reversible. I don't have a formula for the reversible Q, but I have a formula for the reversible work. So let me do this, because it's leading to my thinking here instead of being equated to this. Because it is perfect and isothermal, okay, get that abbreviation, then my Q reversible, Q and W are equal and opposite, right? Because their sum has to equal 0. So I should say, let's insert here, then delta U is equal to 0, and therefore Q plus W equals 0. That's where I'm going there. So then Q reversible is equal to my equal and opposite work reversible. And I know that work, the normal formula for work is minus nRT ln V final over V initial. And so the negative work is actually going to be the positive, nRT ln V final over V initial. Got that? Okay. So work is minus nRT ln V final over V initial, but in this case I'm looking for the negative value of the work because I'm actually looking for Q reversible. Okay, so that's that. So now I can take this, my ds is actually equal to my negative value of d work reversible over temperature, and that, well, that's my formula. And so I think what I'm ready to do now is to integrate. And when I integrate those, move this out of the way. When I integrate those, I get delta S for this second step equal to it's just going to be work, but instead of, sorry, I didn't mean to write that again. It's equal to the negative value of my work over T, which is equal to nRT ln V final over V initial all over that constant temperature. Yeah, the T came out of the integral sign because this is isothermal. So now that goes away, and that's really interesting because when you think about this, this is an isothermal compression. And so for an isothermal compression or expansion, clearly the change in entropy is actually independent of temperature, which is kind of weird. So I get now nR ln V final over V initial. It looks like I'm ready to substitute everything in, but let's have a look back here. I need V final, V initial, I'm not given it. Okay, so before we jump to PVNRT over here, which I can do to get V initial, PVNRT over here to get P2, let's think about this for a second. In an isothermal reversible compression, in an isothermal, I know that PV is a constant. Okay, so, right, you know that. Can I back up a step one more just to make sure that everyone's really with us here, that PV is a constant? Let's say for state 1, I have that P1 V1 over NT1 is equal to R is equal to P2 V2 over NT2. It's N2 and N1 as well, but closed systems. So then I cancel what is constant, in this case isothermal, so there's my temperature, and see right away. So for an isotherm, PV is a constant. The product P1 V1 equals the product P2 V2. What did I need? I needed V2 over V1, but I see that it is equal to P1 over P2. So in my work formula, or the negative Q, down below, I need V final over V initial. I'm going to substitute in what I know, P initial over P final. Okay, so my delta S is equal to NR ln of P initial over P final. I'm going to use 1s and 2s to correspond with the labels I gave above. And here we go, 3 moles. The R, 8.3145 joule per kmol. And I see right away my units of joule per Kelvin are going to come out because the rest of this is unitless. And whereas temperature needs to be, of course, in Kelvin, pressure could be any units because the interconversion among those units involves only multiplication, therefore it preserves the ratio. But you see, because temperature conversion from Celsius involves addition, it doesn't preserve the ratio. P1, 1.00 atmosphere, and then this. Again, strike those, so I'm just taking the ln of the number. So, yep, I did 1 divided by 5 on the calculator for all to see. 0.2 ln times 8.3145 and 3 times that. So I've, oh, look again. It's, is that a negative 40? Hold on. See right here where I did the ln? So it's, yeah, I thought it was M underlined, but of course, when you take the ln of a fraction, you're going to get a negative number, right? Yeah. So maybe when you do the ln, I'm just thinking of the exam and checks and balances. Whenever you take the ln of something, glance at the calculator result, even if you're not finished, and just to make sure is that positive or negative. Okay? Just so we don't miss. Right, I forgot what the answer was, so I'm going to do it again. Times 8.3145 times 3. Right, so that was equal to, this delta S is equal to a negative 40. I get 40.145, so I'm going to report that to 3 significant figures right away. 40.1 joule per Kelvin. Now I'm going to add that extra label that we had. Let's pull down the 18 from up here and add them together. So the answer to the question completely now is the delta SI plus the delta S double I. And so that is a positive 18.0 plus a negative or minus 40.1. And it's all in joules per Kelvin. So I have basically 18. And that minus 40.1. Yeah, the difference is 22.1. Minus yeah, that's fine. I was just checking something else because I had done the problem and I was just checking my final answer and it was different, but it's because we're doing A and I had done B. But that's good. You can put this away and do B after some time, so it doesn't feel like you're just reiterating or memorizing. You should be able to do the B part and check your answer with me if you like. The last part of this, yeah, so you see the net effect is actually a negative. So they ask you to rationalize your answer. So why is it negative? Why is it minus 22? Let's go back up. Yeah, so here we go. Here's the bigger question in these exercises. The perfect gas is increasing by 100 degrees Celsius. How can the entropy be negative? That's what you need to rationalize. So you want to think about that. Think about these changes as being net effects. And here, this is the net effect that you calculated, is really the sum of both of these steps. So I think to rationalize, you'll have to compare the change here with the change here and talk about overall. And while yes, the temperature is increasing, we've actually had a compression, and so you have an amount of disorder, change in order or change in disorder, however you want to describe it, associated with one step versus the other. The net effect is that we actually go to a state of lesser disorder. But again, you'll want to carefully articulate that. I'm just giving you some ideas. But that's the direction you would take. So be prepared to rationalize these answers. Okay? That's a really good question. I'm just thinking now before I sign off on the video. We were just asked to calculate delta S, but think about the other things that we've done, Q, W, delta U, delta H, and so on. This is a really good question to think about that. And also in steps. Really, really good question. Okay, well, let's leave it there.